Hello everyone and welcome back to the channel. A few weeks ago, Microsoft published an article about a mass email campaign by a threat actor called Nobelium. This is the same threat actor behind the SolarWinds attack, the Teardrop, the Sunburst, and the Golden Max malwares as well. We will begin the video by analyzing the three malware samples which are available on VirusTotal and are mentioned in the article. The fourth malware sample, also known as Vapor Rage, is not available on VirusTotal or any other public forums. It is, however, embedded inside a PDF file. We will repurpose the malware's code to extract the DLL from the PDF file and then we will analyze it. So let's dive in. Alright, so here I am in my virtual machine. I have this folder called Nobelium. Inside it, I have two folders. This is the folder which has the first file, which starts the infection chain. So let me open this in Visual Studio Code. This is actually an HTML file. The name of the file is actually nv.html. So let me make a copy of this file quickly and we'll start the analysis. Rename it to nv1.html. All right, so when we look at this file, let me first do a bit of tidy up as well. When we look at this file, we can clearly see a couple of sections. The first one is this section here, and the second one is this script. There are two lines of interest for us in the first part, and the first line shows that a file is being accessed, looks like it is being accessed from an SMB share, and the second one is another file being accessed via HTTP. Now, the reason for the threat actor to use this is possibly get the NTLM hashes of the user, and using this, I think the threat actor is hedging his bets in case SMB share access outside the network is not allowed. HTTP is definitely allowed, so this will allow the threat actor to understand that the user has opened the phishing email or the HTML file which was sent to the user. So we can see this in action, right? So I can open up my virtual machine. And in the meantime, I will change the IP address. One 192.168.181.130. This is the IP address of the Kali Linux machine, which I'm just about to boot. All right, so let's see if we can connect to this. We will run responder on our Kali Linux box, and responder will help us intercept the NTLM hashes which are sent by the system. So let me first increase the font. And before I do anything, I want to configure responder quickly. So let me look for the responders config file. In this file, I want to set up HTTP as off because I'm going to run an HTTP server via Python. So sudo, firstly, let me confirm the IP address as well. Okay, that's fine. Sudo responder -i eth0. Started running, and in the next window, I will start the Python HTTP server. All right, so if it works fine, we should see some hashes here because the user system will send the hashes to access the SMB share. And here we should see the access of the the image file, the second image file. So let's run the file now. I will remove the script part to avoid unnecessary confusion. And the file is opened, and we can see those two images could not be fetched. And we will see here, we can see that the img test.jpg file was fetched. It is not there, but we got the IP address. And here we can see the NTLM hash, which was sent by the user as well. So we confirmed our beliefs that this is the reason why the threat actor had put those lines in there. So now we move on to the analysis of the next part. I will just press Ctrl Z to bring back that part of the file. Now let me try to format the file and see if we can do some beautifications. I will quickly format the file as well, just to understand what I'm dealing with. All right, so I think the formatting is done. And I can see here that this is a long line, and this line is then being used here. Each character is XORed with the number 2, and then most probably this ends up becoming a base 64 string, which is then decoded here using this. And after that, a blob is created from this string, which is the decoded base 64 string, and it ends up becoming an img file. So let's see this in action as well. I will put the word wrap back in and copy this text. So I will copy this text and put it in CyberChef. In CyberChef, I will XOR it with the number 2 first. And we have a base 64 string here. Now I will base 64 decoded. And we can identify the file type here as well. Detect the file type. We'll put it here as well. And we can see that this is an ISO file. So remove this, and now I'll download this file. Save it as download.dat, which is fine. We will move the download.dat file from the downloads folder to our malware folder and rename this to nv.img. Let's see what's inside this file. Once we access this file, a drive is mounted, and we can see it here. It contains what looks like a shortcut. So let's look at what the shortcut is trying to do. The shortcut is trying to execute cmd/c start boom.exe. So it's trying to run a file called boom.exe, but I don't see any file called boom.exe. So let me view the hidden files. And when I view the hidden files, there is a boom.exe here, and there is another folder called nv. So let me first start with the analysis of this boom.exe. Close this folder. Close Visual Studio Code for now. Move it, the sample, to the malware folder. And we will remove the hidden attribute. I will drop this in PE Studio. So PE Studio tells me that this is a .NET file. So we can easily open up this .NET file in dnspy. Let's do that. Drag and drop. Let's go to the main function. When we go to the main function, we can see it is looking for a directory called nv, which was there. We saw it. It is here. And if the directory is there, it will open it up in Explorer. The next thing that it is trying to do is it's checking for a path. So application data, it's looking for a path or the existence of a file in the app data folder, and the file is Microsoft native cache service.dll. If the file is not there, it will go through this process, and over here it is doing some basic reconnaissance of the system. It is getting the host info, the host name, the domain name, the address list, etc., etc. And based on that, it creates a string. If the string is not null, which means there is something in there, it will run this function AES script, right? Let's see what this is doing. It is creating an encryptor and looks like it is encrypting this string which is provided. After the string is provided, it is running this upload function somewhere, and the upload function looks like it accesses the Dropbox API and uploads this file. If you look at the parameters that are passed to this function, we can see what looks like an API key, and these two underneath are the parameters required for encryption or decryption of AES. All right, after it has done basic reconnaissance of the system and uploaded the file, it executes this add rule function. Let's go in there. In the add rule function, it is looking for some folder, Microsoft native cache, and it downloads a file. So again, it's downloading a file from Dropbox API, and the file's name is, it's in the folder called TMP, and the file name is manual.pdf. And after that file is fetched, looks like a DLL is hidden inside this file, and this method is being used to extract that DLL. As discussed earlier, we are going to use this piece of code to extract the secondary payload from the PDF as well. So let's go on. After that, it is setting up some persistence here, and the persistence value that it is setting up is run DLL 0 and 1. 0 would be the DLL name and 1 would be the function name. So DLL name is native cache.dll, and the function name is _config native cache. The next thing that it is doing is it is downloading another file which is called tmp/readme.pdf, and array3 is created from there, and looks like another DLL is extracted from the readme.pdf. And after all of this is done, if the native cache service is present, then it is started here. All right, so I think the next step would be for us to analyze the native cache service.dll. But before that, what I want to do is I want to show you the function, the code, which I will use to extract the DLLs from the manual.pdf and the readme.pdf. I want to extract both of these DLLs together so that we can move on with the analysis of the DLLs together in Ghidra as well. So let me open up that code and we'll continue the video.
3 days later.
All right, so I've copied the code and the PDF files in this folder. Let's open the code, decode Nobelium PDF. In the main, you can see that there are two function calls to decode file, and the file path is being provided to this function as a parameter and output path. So in the first one, I'm providing manual.pdf, and the second one, I'm providing readme.pdf. And the first one, the output is going to be native cache SVC, and the second one is going to be cert PKI provider. As I said, this file is currently present on VirusTotal. This file is not present on VirusTotal, so we had no option. We had to write this code to extract it from the readme.pdf. So anyways, let's run this code. This is the code which I have extracted from the malware itself. If you remember, in the malware, it was extracting the DLL files from the PDF itself. So let's run the code, get the DLLs, and then we'll open them in Ghidra quickly. All right, the execution is complete. We should have those DLLs created. We have those DLLs created. So let's close this and move on to Ghidra. I will add those two files in Ghidra, create a project, and I will resume this video. All right, so we can open up those DLLs now in Ghidra. The setup is complete. So we'll start with the native cache svc.dll. We'll go through these very quickly. So the function that was being called was the config native cache function. If we look at the native config cache function, we can quickly see that there is a create process A here. The process that is being created is from this string. This string is being created from most probably here. It is being passed in this function, which looks like a wrapper to a vsprintf function. So basically it's concatenating some strings and it is recreating this, it is creating this executable string. So it should be run DLL, then a DLL name, and then the name of the function. So you can quickly look inside the assembly and figure out what is being set here. We can see run DLL here. So this looks like the function name, which is egl get configs. And if we go up, we see that this is the name of the DLL which is being passed to it, and the DLL name is, so it's exactly the name of the file that we have, certpki provider.dll. So it looks like this native cache svc.dll is basically creating another process which is run dll32 with the cert pki provider.dll, and the function it is calling here is egl get config, right? So let's close this and go to the cert pki provider.dll. Insert PKI provider, if you remember, egl get configs was being called. If we open this function, we can see a reference to the native cache svc.dll, and it looks like a path is being created here, swprintf. So get folder path and the path. So I think this is var underscore native path. The native path is being sent to this function. Or let's open this function quickly, and it is getting the attributes of this file. And it is setting up this variable. I think this is mw underscore get file attributes. So this, and this looks like var underscore check var underscore file attributes. All right, if the file attributes is not equal to 0, I'm assuming this is checking for the presence of this file. And so some variables are being created here. Destination, this function. All right, so this function is doing malloc. So let's rename this to mw underscore wrap underscore malloc. So 3 variables are being created here, and those memory for those 3 variables are being set to 0 here. The first variable is being passed to this function, get computer name. So we can set here edit function signature mw underscore get pc name, and this one would be var underscore pc underscore name, get username. So I think this would be var underscore get var underscore user underscore name, and we have pc name and var pc name and username being used here. Looks like another variable is being created here, and after that I don't see anything special here. Let's go to this, because this another variable is being passed here which we have not named till now. So go to this function. This looks like a command and control communication function. We can see an IOC here, holes contracting. All right, so we keep on going down. We can see HTTP query info, internet read file, and unrecovered jump table plus this. I think this would be the file which is received file. And once the file is received, some action is being taken here. Let's go to this function. All right, so I can see a XOR happening here. So this looks like the file is being decoded here, and this looks like a key. So we can say that mw underscore decode underscore file received file. All right, so received file is here, and then what is happening here? All right, so it looks like the file is sent here as param1, and then param1 is being used here in virtual protect. This tells me that this is not a file, or this buffer contains some kind of a shellcode. So I will rename this to say that this is var underscore received code. So now we have received code. We are running a malloc on this, a virtual protect on this code. Wrapper of virtual protect. And we see here that we were correct, that this function, this code is being executed. A pointer to this code is being used, and it is being called as a function. And after that, a close handle is being called. And I think after that, the execution will be passed on to this function, and it will continue from there. So I think we've spent quite a bit of time in the analysis of the artifacts. I think that brings us to the end of the video. I hope you enjoyed the video, and I will see you in the upcoming videos. Thank you very much for your time.